Okay, good afternoon, ladies and gentlemen. Can you hear me?
Yes, we can.
Okay, thank you. So it is my pleasure to introduce a new series in the TMS webinar series. And this is going to be one that deals with the COVID-19. And today will be the first of a few seminars on the topic. They will not be necessarily in line. So next week we will have another topic, but we will have at least 3 or 4 of this webinar about COVID. So they will be collected in our YouTube channel and on the stream page. So if you know a friend that might be interested, you can share the link with them. And I see that we are already 74, so very good attendance. Thank you for being here. And I will now pass the ball to Denise, who will introduce our guest for today, Andrea Palladino. Thank you.
So good afternoon, everybody. I hope you can see and hear well. This is Denise Boncioli speaking, and it is my pleasure to introduce to you Andrea Palladino, who is the speaker of today. So Andrea is an astroparticle physicist. He was actually a student at the Department of Physics at the University of L'Aquila, where he had the master degree in 2014, working with Professor Villante about oscillations of high-energy neutrinos. After that, he moved to Gran Sasso Science Institute, still in L'Aquila, where he got his PhD in 2017, working with Professor Vissani. After that, he went to DESY in Germany, where he's still at the moment, where he's a postdoc, and where we also had the opportunity to collaborate together within a project for studying the origin of the cosmic rays and neutrinos. But actually, today, Andrea wants to tell us about his analysis on the current COVID-19 issue, and this is what we will hear today. So thanks, Andrea, a lot for accepting our invitation. And I also kindly ask the people who want to have questions at the end to write them down in the chat. So please, Andrea, you can start.
Thanks, Denise, for the introduction and for the invitation to you and Marco. So I'll share my screen now. Okay, can you see the screen?
Yes, thank you.
Okay, good. So I will talk today about modeling of the COVID-19 pandemic using a revised version of the Serum model. And the talk will be divided basically in 4 sections. In the first section, I will give some elements of the theory behind this model. And then I will present and discuss the data of Italy. And then I will compare the model with real data. And at the end, a brief introduction to what is the situation in Europe. So the Serum model, if you search on Google and you write Serum model, the first page that you can find is the definition of Wikipedia. So the Serum model is one of one of the oldest model that was invented for modeling the expansion of the spread of a pandemic. And it consists basically in 3 categories. S is the number of susceptible people, so people that can still contract the infections. I is the number of infected people, and R is the number of removed people. So it means people that are immune plus deaths. This model was invented, it was proposed for the first time in 1927 by Kermack and McKendrick, both Scottish. Kermack was a biochemist, the other one was an epidemiologist. And this model is based on 3 differential equations. So don't be scared about this slide. I will try to explain what does it mean. So the first equation that you see is the variation of the susceptible people in time. So we start that all the population is susceptible, so all the people can be infected. Of course, while people get infected, so while people go in category 2, the IDT, the number of susceptible people becomes smaller and smaller. And the parameters beta determines what is the speed of the epidemic. And the second equation, we see that there is another parameter that is gamma E, and this parameter gamma says what is the average duration of the illness. Particularly gamma to the -1, so 1 over gamma gives roughly the average time of duration of the illness. And then there is the third category. So people after a certain time, gamma to the -1, people go in the category R, and in the Serum model there is no separation between deaths and recovered people. So what is called R, it's the sum of deaths and recovered people. And this is a system of differential equation in which we have the condition that the sum of S, I, and R is preserved in time. So this sum is constant and it's equal to N, that is the total population. So we have N, that is the total population, S is the number of susceptible people, I, the number of infected people, and we have basically 3 free parameters that are beta, gamma, and N. But N is fixed on the population. So we have really 2 parameters that we can change to model the spread of the epidemic. Now I will show some example. We will start with a very basic example in which we have just 1 infected person. And so the susceptible people are the entire population -1. And R0 is 0, so it means that no one is immune because there is just 1 infected people at the beginning. And let's see how the system evolves changing beta and gamma. So there is a website in which you can do that yourself if you want. The link is on my slides. And here I summarize again that beta regulates the strength of the virus spread, and gamma to the -1 gives the duration of the illness. In this website, you can change beta, gamma, and all the other parameters, so you can repeat the simulation yourself if you want. And at this point, it's interesting to introduce this parameter R0 that is very often discussed in these days. R0 is a combination of 4 elements of the Serum model. It's the product of beta times S over gamma times N. So since most of the population is still susceptible, for the moment, it's a good approximation to say that R0 is equal to beta divided by gamma. If R0 is larger than 1, it means that the number of active infected people increases. If R0 is smaller than 1, the number of active infected decreases. And this can be represented in this way to understand better what is the meaning of R0. And R0 gives information on the number of people that can be contaminated by a single person. So, for example, if we start with R0 equal to 2, we have 1 infected that infects other 2 people, and then we have 4, then 8, then 16. So I ask a question at this point. If you want, you can answer in chat and we discuss at the end. So what's the time to contaminate the entire Italy having a constant R0 of 2? So this can be interesting to understand why it's important to have restrictions. And here we have R0 of some diseases, some common diseases. So you can see that R0 can go from very low values, like between 1 and 2 for the seasonal influenza, but can be also very high for some illness like measles, for example, which is much larger than 10. Let's see some example of the Serum model. So let's fix the characteristic duration of the illness to 14 days. So it means that I take gamma equal to 1/14, one infected at the beginning. And on the left panel, we have R0 equal to 5. Middle panel R0 equal to 3.5, and right panel R0 equal to 2.5. So as you can see here in left panel, we have a peak after 30 days. And in this peak, half of the population is contaminated. In the rightest panel, we have a peak much later, and we have just 200 people contaminated at the peak of the infection. At the end, in both these three cases, all the population get contaminated. But it's important to notice that the position of the peak changes, changing the R0, and it's very important to notice that the total number of people at the peak is very different. The number of infected people is very different. And of course, this information is crucial because if we have hospitals with limited space, we want to reduce the number of infected people at the peak of the epidemic. Now we analyze another scenario in which we start with already some infected people. We have a population of 1,000 people here and 300 of infected people. 100 have already recovered. It's just an example, but you can see here that if R0 is larger than 1, left panel, the spread, the function is still increasing. It reaches a peak and then it decreases. On the rightest panel, we have the opposite situation. R0 is equal to 1, and here we observe immediately a decreasing of the epidemic. So what is the limitation of the Serum model? The most important limitation is that once we fix beta and gamma, we have a certain R0, and this R0 only evolves in time following the susceptible people. So it means that while people are infected, the number of susceptible people decreases, and as a consequence, R0 decreases. But in this way, R0 decreases very slowly. It means that R0 does not take into account effect of restriction, effect of lockdown. These effects are not included in the Serum model. So what we tried to do, and when I say we, I refer to the Covid team. This is a team that was born during the epidemic. There are many people with PhD. There are people from different fields, from physics, from statistics, from philosophy. It's now a large team. We were just 3-4 people. Now we are already more than 20. And what we did, the most important change is that R0 now is beta times S over gamma over N, but there is another important element. So R0 decays exponentially in time, decreases exponentially in time. So what does it mean? It means that after a certain time that we define as a time threshold, after this time we say, okay, from this moment R0 decreases, and this T threshold can be interpreted as the time in which the quarantine started. Tau is the parameters that regulates the speed of decaying of R0, and so now we have the model that is given by 4 parameters, not only beta and gamma, but we have beta, gamma, tau, and time of threshold. And if you are expert in coding and you know how to use Python, you can see directly these codes are public, are on my repository, and there is also an official repository of Constants. But okay, for the moment, let's focus on the model. Another important information that is contained in the model is the information on asymptomatic people, because it's known that there are also people that do not show symptoms, and it's important to take into account these people. This number, on the other hand, it's very, very uncertain. And in our model, we are using the estimation done by Dr. Ilaria Capua, and she says that 2/3 of patients might be asymptomatic. So it means that the total number of infected people might be 3 times higher than the official numbers reported in, usually in television, in journals. And if we see other studies, for example, the study conducted in the population of Voioganio, that was one of the first places with lots of infected people. This study shows that 43% of people who were tested positive to COVID do not show symptoms. And then we have an extreme study conducted by the Imperial College that it's much more extreme and shows that 6 million of people have been already infected. However, this case looks very extreme, because if it's true, the fatality rate would be equal to 0.5%. Then it's very hard to justify why the intensive cares were so stressed in Italy, why the it's a very extreme scenario. I did not see other studies that talk about this very large number of infected people. Okay, so let's go to present the data. The data are updated to the 4th of May, so it's 2 days ago. And this is the situation in Italy. We have a total number of cases that it's above 200,000. The number of recovered people, it's 82,000, and number of deaths is around 30,000. Probably it's 30,000 now. And as you can see here, the curve of total cases is still not flat, so it's still increasing a bit. So it means that we are not at the end of the epidemic. And I would like to discuss this mortality rate versus fatality rate, because every day I receive questions about this. I want to clarify in this talk. So the mortality rate is the number of deaths divided by the total population. The fatality rate is the number of deaths from a certain disease compared to the total number of people that got the disease. So the fatality rate is the number that usually you hear, and this number is usually computed in this way. So they take the number of deaths, they divide the number of deaths by the total number of cases, and they got this number 13 times 13.7% now. Okay, so this calculation is wrong. It's wrong for a very basic motivation, because it assumes that all the other people will recover. But of course, we don't know anything. So we should now fix this 200,000 cases. We should wait until the end of the epidemic, and we should see how many of these people would die for COVID. This, of course, would increase the fatality rate. But on the other hand, we have also another important ingredient, that is the fact that asymptomatic patients exist, and of course they are not taken into account in this calculation, and this would decrease the fatality rate. So in conclusion, the fatality rate is very hard to estimate right now during the epidemic, and so I suggest to not give so much importance to these parameters, that it's very affected by a very large uncertainty. This is an histogram in which you can see the cases for each region. The cases are normalized to the population. We see the number of cases for each for 1,000 people. You can notice a strong asymmetry between north and south. For example, in Lombardia, there are 8 cases each 1,000 people. If we go to a smaller region in the south, for example, we go to my region, that is Molise, it's just 1 every 1,000 people. Abruzzo is similar, is 2 every 1,000 people, so numbers that are very, very small compared to Lombardia. We talk about factor 4, factor 8 in some cases. And also other region of north of Italy have a lot of cases compared to the population. You can see Piemonte, for example, Valle d'Aosta. This is the number of tests for each region every 1,000 people. The average is 40 tests every 1,000 people. And as you can see here, for example, Lombardia is on the average. So I heard more than one time that people saying in Lombardia there are more cases because they do more tests, and this is absolutely not true. The number of tests done in Lombardia is exactly the average of the tests that are usually done in Italy for the moment. Up to now, so more than 2 million of people were already tested. And this is the number of daily cases. So let's focus on this because so this is the incremental function. So it says how many new cases there are every day, how many new recovered, and how many new deaths there are every day. And if you look at this curve, it looks that the peak of the epidemics was on the 20th of March. This is not true. This is just the peak of the derivative function. So if you remember from mathematics, we have the cumulative function and then we have the derivative. But if the derivative reaches a peak and then it decreases, it does not mean that the cumulative function will decrease. So when we go to this function, this is the important function to understand the behavior of the epidemic. And this is the total number of infected people, active infected. It's what usually the data from Protezione Civile are called attualmente positivi. So this is people that are really infected in a certain day. And this curve is obtained subtracting from the total case, the number of recovered people and deaths. And as you can see here, the peak was on the 20th of April. With 108,000 of people. So if you compare this number to the day of the lockdown, you realize that we have much more infected people now, because at the moment of the lockdown was 80,000. But we have also to take into account that the effect, you can see the effect after roughly 2 weeks. And after 2 weeks from the lockdown, the number of infected people was already around 50,000. In this plot, I show the number of people in intensive care. This is divided in 4 macro regions. Upper left is north of Italy. Then we have the center, south, and the islands, so Sardinia and Sicilia. So as you can see here in the north, we were close to the saturation of the places at the end of March, but now the situation is much better generally in all Italy, and all the people, all the intensive care are okay, not empty, but we are well below the threshold. And this is the behavior of R0, so the parameter that we discussed at the beginning of the presentation. As you can see, at the beginning it was very high, was around 5. Then it started decreasing, and now is around 0.94. This was updated to 2 days ago, because yesterday there was a very positive day with minus 5,000 in the number of infected people in Lombardia. So it means that on average, we are below 0.9 now. I don't remember the actual value. It should be something around 0.89 probably for Italy. And this is the map of R0 in different regions. So the regions in green are regions in which the R0 is smaller than 1, so the epidemic is decreasing. The R0 calculated on Covstat for regions is based on the last week. So we take the data of the last week and we compare with the model, and we extract the R0. And there are still few regions in which R0 is larger than 1, that are Lombardia, Sicilia, Puglia, and Piemonte. And this is the fatality rate per age. This is taken from one image of BBC. So as you can see here, probably you already know, the fatality rate is very, very different for different ages, and it becomes quite high, 15% for people above 80 years old. Okay, at this point we have all the elements to compare the model and data. And let's start this comparison, recalling some elements of the model. So we have the parameters beta that regulates the strength of the virus spread. Then we have gamma to the -1 that gives the duration of the illness. Then we have tau that says how R0 changes in time, and time of threshold that denotes the time in which R0 starts decreasing. What we do is that we take the model, we take the data from Protezione Civile. This data are released every day, and the first day of the data set is the 24th of February. And when we compare the model with the data, we can find the ideal parameters to reduce the discrepancy between model and data. And those are the ideal parameters that we found. To have an idea of what tau, okay, first of all, gamma 0.048, if you do 1 over 0.048, you obtain roughly 20 days. So it means that the model indicates an average duration of the illness of 20 days. And tau 25.8 days, it means that after 26 days, roughly, R0 becomes R0 over E, where E is the number of Nepero, and it's equal to roughly 2.7. And this is the comparison between our model and the true data. So you can see the true data in red, and then we can see the model as a dashed blue line, dashed blue curves. And for the moment, the average error on the previous data, on the past data, is 4.7%. So as you can see here, there was a time in which true data were above the model, roughly in the last week of March. And now again, the true data are a bit above the model, but the discrepancy on average is 5%. And so does the model work? This is probably the most important question. Is the model predictive? I report in this slide the abstract of a seminar that I gave on the 9th of March, so it was 2 months ago. In this abstract, I also gave some numbers, and I say the peak will be reached at the end of March, beginning of April. And the day of the peak, we will have order of 10 to the 5 people, so 100,000 people infected. And this scenario would result in a number of deaths between 20,000 and 30,000. I think the real situation is very close to what was expected 2 months ago using this model, because the true number is at the peak was 108,000 infected people, and the number of deaths is probably now even more than 30,000. So from this side, it was probably too optimistic. We predicted the peak for the end of March, beginning of April. This was not correct, because the real peak there was 2 weeks later, roughly. But I would say that staying on the numbers, on the absolute numbers, we did already good prediction 2 months ago. And here we report some future estimations. So those are not prediction, and it's important to clarify this aspect. This is just done in this way. We fix a certain R0 on the 4th of May. And then we see, in looking at a certain interval of R0, what we can expect in the future. But R0 is fixed on the 4th of May. So then R0 just decreases when the number of susceptible people decreases. And as you can see here, for R0 smaller than 1, the number of infected people decreases. In a very optimistic case, for the beginning of July, we should not have any more infected person. If we go to R0 between 1 and 1.1, there is the risk to have a second peak of the epidemic, like very similar to the old one, to the previous one. If R0 is larger than 1.1, and we can have a second peak with much higher numbers. So it's important to monitor R0 and to check if R0 goes again above 1 to immediately try to take control of the situation to avoid this dread scenario, of course. And this is the situation in Europe. You can see here the map of the rest of the Europe. There are some red countries now in which R0 is much larger than 1. In UK, the situation is particularly, the epidemic is increasing fastly again. In Italy now, we are below 1. In Germany, we are much below 1. I will discuss in the next slide the situation in Germany. So yeah, you can see that the situation is not homogeneous at all. There are a lot of differences between different countries. I would like to put the focus on Germany for 2 slides, because probably you heard this news that in Germany, most of the Italian newspapers said in Germany, the lockdown was released and cases increased again. So is it true? And to answer to this question, I want to show you the epidemic curve of Italy and Germany. So the orange one shows the number of infected people in Italy, and the blue one shows the number of infected people in Germany. As you can see here, there was a peak in Germany at the beginning of April, and then the number of infected people started decreasing. The phase 2 started roughly on the 20th of April. It means that from that day, some shops are opened again. We are going back to the normality very slowly, but we are going back. But as you can see here in this plot, there is no increasing. So what really happened in these days was that there is an institute in Germany, that is the Robert Koch Institute, that gives every day the range of R0. So the range of R0 was calculated between 0.7 and 1 at 95% confidence level. This range for 1 day went to 0.8, 1.1. So there was a slight increasing that from the point of view of statistics, it's not significant, because as you can see, these 2 intervals are compatible. And then this R0 went back to its value of the previous days, and nowadays it's even smaller. It's between 0.66 and 0.89. So there was no increasing of infections in Germany. And yeah, this is just to clarify what's the difference between the real news and what was interpreted by the Italian newspapers. And here you can see the situation in the world, but it's not really in the world, it's in the Europe, sorry, wrong title. And here, yeah, you can see that United Kingdom is still increasing very quickly. Italy is more or less like France is start decreasing, also Spain is decreasing, and Germany is decreasing very quickly. Half an hour, so thanks for attention, and yeah, I will answer to your question.
Well, thank you very much, Andrea. We ask people to switch off their microphones, please. Okay, so I think we are having already some questions,
Yep.
but I don't know if you wanted first to comment on your question you asked before, because
Yeah.
I don't see comments on that. So maybe you want to say something.
Yes. Okay. What I have to do? I continue sharing my screen, Denise, or
I think it's fine if you share the screen. So if you want, you can start with your.
Yeah, I hear another voice in the background.
Sorry, please switch off the microphones. Thanks. So please, Andrea.
Yeah. Okay. So the question that I did, it was related to this slide. Okay, if R0 equal to 2 and the spread is free, so there is no measurements, no constraint, nothing, no restrictions, it takes just 26 days to infect the entire population. So 26 days to infect 60 million of people. So from this number, I think you can understand that it's very important to stop and to reduce R0 because in 26 days it's a very short time, and I think there is no country in the world that can manage this situation.
Thanks a lot for this for this example. So we are having already some questions. I can read for you. So Marco is asking, is commenting on the fact that the model is based on the fact that infected people who heal become immune. Should the fact that your predictions are so close to reality be considered as an indication that infected people become immune? Is there any biological proof that you know on the matter?
Okay, so for okay, first of all, the bad news is that I already know that from China and probably from Japan, from China, I'm sure there are cases in which people were infected again. So the bad news is that it seems that it's not guaranteed that people that got the illness are really immune. The good news is that this fraction looks for the moment small. There is not enough statistic to do this study, but it looks for the moment small. I don't remember if it was 1 people over 1,000. So please check this number, but we are talking about very small fraction. From the model, I would not say that we can say that just from the comparison between model and data. No, I don't think we are so sensitive to this variation.
So basically, I guess there is not enough study yet.
Yeah, there is not enough study.
And enough statistics, I guess.
Yeah.
So, and then Yona is also asking something about the population size. So she's asking, so your model is used for a fixed population size.
Yeah.
So are there any models which exist for leaky systems? So if people move into or out of a country or area, or are these quantities of people too small to consider or cancel out?
Yeah, there are some models, there are some evolution of the Serum model. This model, there is one model that is called SEIRD, S-E-I-R-D, in which we have susceptible people, exposed people, infected, recovered, and deaths. So people that die are removed from the system, and there is also another term that contains people that are born. So there is a dynamic system. On the other hand, we are studying this epidemic on a time scale of, let's say, 3 months in total. I don't know. We started 2 months ago. Probably we will study for 4 or 5 months. And in this short period, this should be totally irrelevant because we are talking about a total population of 60 million of people. So even if we have, let's say, I don't know, 500,000 of people that left Italy or that die, that it cannot change anything on the model.
Okay, now we have, I think, a more social question about still from Marco. So do you think reputable media are using fake news, such as the one you mentioned about Germany, to scare Italians into behaving better?
So I would not say fake news. The problem is always the interpretation of the news. So as you can see here, there is something true. No, there was an increasing of this index from an interval of 0.71 to the interval 0.811. But what I've read on the Italian newspaper was very different. I've seen the index went from 0.7 to 1. And this is completely not true. So I don't know if it's really fake news or it's just an interpretation of. Okay, for example, another example is yesterday. Yesterday there was a news that Molise had the largest R0 in Italy. So of course, all the people that live in Molise, in my region, or my parents, called me because they were very scared about it. But what's the situation is that so the R0 is not the only parameters to see what happens. No, if you look at this plot, we have the number of cases for each region. So when you look at Molise, it's just 1 case every 1,000 people. Compared to Lombardia, is a factor 8 less, factor 7 less. So even if for 1 day or 2 days the R0 of Molise is the largest, it does not mean anything. So it's it's always the way in which this kind of news are interpreted that it's a bit risky.
I guess still on the same issue, sometimes they take the R0 plus or minus, so they just I've seen that sometimes they
usually they always show in television or in newspapers the average value of the R0, but we don't know if the uncertainty is 100%, 10%, or 200%. This is usually not reported in the...
So, yeah, errors, of course, matter in this case. So we have another question still about R0. How much can the increase in death affect R0?
How much the increasing in what, sorry?
How much can the increase in death, in number of deaths, I guess, affect R0?
Okay, so if we go to this equation, so for the R0, the equation that is relevant is the second one. So R0 is obtained by a combination of beta S and gamma. So when R0 is smaller than 1, it means that new infected people are smaller than the sum of recovered and deaths. So if we have a lot of recovered people or a lot of deaths, the R0 will go below 1. So the system does not distinguish between, as I said in the previous slide, in one of the first slides, it does not distinguish between deaths and recovered people. So both people are immune because they are removed from the system. So R0 is smaller than 1 when the new infected are smaller than the sum of deaths and recovered.
So thanks. We go on with the questions with this one. What do you think about the treatment of COVID-19 with ivermectin?
I'm totally not expert in this field, so I cannot give any answer. Sorry.
So next one is by Professor Tetti. She is asking, what is your message to young scientists beyond the specific COVID-19 situation? How can we teach them to distinguish between correct numbers and incorrect numbers?
I think especially for people that study scientific matter, they should always be curious about news. They always should try to think in independent manner if something it's true or not. And I think all the people that study scientific matters can really do that. They have the mind that it's ready to do that, and it's important to do because especially now with social networks, it's full of fake news, and usually fake news are also shared much more frequently compared to true news. So it's a very delicate moment. We need really to think with our brain sometimes.
So next question is, do you have any explanations for the discrepancies between your model and the statistics? And how can you improve your models based on the data you obtain?
Between our model and what?
And the statistics, I guess, the data you have from the Protezione Civile, for example.
The discrepancy, you mean this the 4% of discrepancy, this one?
I guess this is the question.
Or you refer to the discrepancy between our model and the Istituto Superiore di Sanità? No, I don't know.
I guess the question is about the error that you find and how reliable is your...
Okay, so the error is 5% plus minus 5%. So it means that in an interval of 15%, basically we have all the points of the simulation. I don't think it's possible to improve this model using. So if you see here, basically this model depends on 3 parameters. It's beta, gamma, and tau, because the time of threshold is 0 at the best fit. So it means that R0 started immediately to decreasing. So we have a very complex phenomena, and we have just 3 parameters to interpret this phenomenon. So I don't really think with this model, we can do much better than this. So it's probably, I would be surprised to get a smaller error with such a model.
So okay, next from Michela, she's asking, she's saying that there are people that are positive for more than 30 days. So
Yes.
she's asking if this could alter the gamma parameter in the model. So on a practical level, what would that entail?
So these gamma parameters is, of course, is a sort of average parameters that comes out directly from the fit, so from the comparison between data and the model. In a more advanced model, of course, we should not take gamma as one number, but probably we should do something more sophisticated, like using a distribution of gamma, like, I don't know, a Gaussian distribution with some average, 14 days as an average with a longer Q. So this probably could have some impact on the model, because, of course, if people are sick for 30 days, the curve of infected people will be higher compared to what we have now. On the other hand, we have also always to see how many people are really sick for 30 days compared to the total number of cases. And so yeah, probably, because when you introduce this distribution, then you have also to consider that there are people that are sick for less than 20 days. So I cannot say now what would be the impact on the curve, but of course it's an aspect that it would be interesting to investigate.
Next question is about if the model can be adjusted to account for the age.
The model can be adjusted to account for the age. Yes, the main problem is that nobody had time up to now to do that, because this is for all of us. It's a side job. We all of us had a main job. It requires a lot of effort to do that, but for sure it can be adjusted. You could, for example, just take these equations for each interval of age. Let's say we take 4 intervals, and then for each of the intervals you fit a different beta and gamma. So you will have a different beta and gamma for each age. But personally, I don't think that it's beta and gamma that will change a lot, but it's the fatality rate that is not included in this model. We are not showing anymore the prediction for deaths in this model. So what you say, yes, of course, it's interesting if we add if we add the deaths. If we add the deaths, at that point we should divide the population in interval of ages.
So next question, is it possible to make accurate predictions on the impact of the easing of the different aspects of lockdown on the R0 value?
Sorry, Denise, can you repeat the impact?
So the impact of the easing of the different aspects of lockdown on the R0 value?
No, I would say this is very, very, very hard to guess, because it's. I mean, if you look at this plot, you can see that we started with R0 close to 5. Then there was the lockdown. It was the 9th of March, right? So the 9th of March, we had R0 4.4. Then it started decreasing. Yeah, but it's very hard to connect directly the R0 with the restrictions. What I can say that we would expect a totally different behavior without any lockdown.
But of course, I guess it is complicated to correlate.
Yeah, I think it's very, very, very hard to correlate. Probably in Germany now they are looking with very much interest to this R0 because they want to tune the restrictions according to the average value of R0. So they want to do the opposite, basically. Given a certain R0, they want to tune the lockdown, but not. Yeah, it's very hard to do the opposite from the lockdown to evaluate which R0 we can expect.
So next question, would it be possible to put a term in your model that takes into account the probability to get again COVID and see how the system behaves at regime?
Yes, this you can do. You have just to put a term in this third equation. So the RDT, you have to put a term in which a minus something proportional to the number of recovered people. And this term, let's say minus, I don't know, alpha R, then you have to put this term here as plus alpha R, because these people become again susceptible. So yes, this can be done. You have just to add the same term in the first and third equation with opposite sign.
So I think second last question is related to restrictions. Do you think we will see an increase or decrease in the value of R0? Maybe it's only related with people behavior, but what is your opinion about that?
I mean, if we see now an increasing of R0, it would not be too surprising. We will not see it now, but probably in 2 weeks. But as for Germany, I mean, there was a slight increasing of R0, but then the curve is still decreasing. So R0 is an important parameter to see in which direction the epidemic is going, but it's not the only parameter. We cannot just rely on R0 to understand what is the spread of the epidemic. So yes, from my opinion, it's possible that R0 will increase again by the mid of March, the mid of May, the end of May. But it does not mean that we have to lock again the Italy or to. We have to see many other elements to see what happens.
So I think we are having the last comment or wish by Professor Tetti that I find very nice at this point. And I think we had more or less the same time for the webinar and the same time for questions. So I guess it was very interesting to many of us. So she's saying that this was a great webinar. And so I'm reading what she wrote. I hope students will become skeptic on data and start thinking independently. The beauty of being a scientist is that we understand better than the lay population. The bad thing is that we do not believe everything they tell us. So
I'm very happy about this comment because it means that I reached my purpose during the webinar.
And I think also that we understood that there is still room for improving the model. So I guess if anybody would like to contribute, you can.
Yeah, of course.
Anybody who wants to contribute can contact you, I guess.
Of course, yeah.
And so the other comments are like a great start for this series of webinars, and they. And people are just, thanking you for this topic and the way you shared your opinions, but also your facts, let's say, with us. So I think if there are no other questions, I guess I see no other. I think we can thank you again. We can't make we can't clap our hands, but please. Take it virtually as just thank you so much for this for your contribution to our knowledge about this, and we really hope to see you and all the other people in person. And with the other people, I think we will have the next seminar in 1 week from now. Thanks a lot, Andrea.
Thanks to you for the invitation, and thanks for the audience for being here today. Bye.